Hello students, today we are going to see about the image formation in convex and concave lenses. Before getting into the topic, we should recollect the basic rules for the diffraction in concave lens and convex lens. First one is basic rules in concave lens. So there are three rules in that. First one is if a ray is parallel to the principal axis, it gets refracted and emerges out as if it focuses through the principal focus. Second ray is the ray passing through the principal focus. It emerges out as a parallel ray to the principal axis. Third one is the ray passing through the optical center, which will not deviate its path after emergence. Next one is the refraction in convex lens. Here again we have three rules. The first one is a ray parallel to the principal axis refracts through the principal focus on the other side of the lens. Second one is a ray passing through a principal focus emerges out as parallel to the principal axis on the other side of the lens. And third one is a ray passing through the optical center of the lens will not get deviated. It just emerges out without any deviation. With these set of rules, we have to draw the image formation diagrams in concave and convex lens. First one is the image formation in convex lens. Here we have various positions of the objects kept in front of the convex lens. So let us see each case separately. The first one is when the object is at infinity. For example, if we focus sun, which is at far away distance from the convex lens, so that object is said to be at infinity. So how will you get the image of a sun when you focus through a convex lens? Since we assume only parallel rays from an object at infinity, all these parallel rays refract through the principal focus of the convex lens on the other side. So all these rays seem to converge at principal focus. So the image is formed at the principal focus of the convex lens on the other side of the lens. The images thus formed have the following properties. The image position is at principal focus. The size of the image is highly diminished and the nature of the image is real and inverted. The second one is when the object is beyond 2f, that is when the object is kept beyond 2f. 2f is nothing but the center of curvature of the lens. So when you place an object beyond 2f, here in this diagram, AB is the object to the left of the lens. And we have to measure the distance between object as U. U is the distance between object and the optical center of the lens. Now we have to consider two rays from the object. One ray parallel to the principal axis passes through the focus. The next ray passing through the optical center passes without any deviation. These two refracted rays meet at a point on the other side of the lens which is beyond f. That is, the image is formed between f and 2f on the other side of the lens. Now A dash B dash is the image thus formed. The properties of the images thus formed are: the image position is between f and 2f, the size of the image is diminished, and the nature of the image is real and inverted. Here in this diagram, V is the image distance. That is the distance between the optical center and the image. And F is the focal length, the distance between optical center and the principal focus. The next position is the object is kept at 2f. So here in this diagram, AB refers the object, and from A we have two rays. One ray parallel to the principal axis passing through the principal focus on the other side, and another ray passing through the optical center will not get deviated, and these two refracted rays meet at a point to form an image A dash B dash. And the properties of the image thus formed are: The image is formed at 2f. The size of the image is same size and the nature of the image is again real and inverted. The next position of the object is between f and 2f. So when you place an object between f and 2f, again we consider the same two rays. One ray parallel to the principal axis passes through the principal focus on the other side of the lens, and another ray passing through the optical center will not get deviated. And these two refracted rays will meet at a point when an image A dash B dash is formed. The image thus formed has the following properties. The image position is beyond 2f and the size of the image is highly enlarged and the nature of the image is real and inverted. The next position of the object is at f. Here again AB refers to the object. From A we have two rays, one ray parallel to the principal axis which passes through the focus. The other ray through the optical center will not get deviated. So when you look at the diagram, you will come to know, or you will notice that the two refracted rays on the other side of the lens do not meet because they both seem to be parallel. So they do not meet. If at all they seem to meet, it will be at infinity. So the properties of the image thus formed are the image position is at infinity and the size of the image would be highly enlarged and the nature of the image will be real and inverted. The last position of the object is between F and O, that is between the principal focus and the optical center of the lens. So if the object is brought very close to the convex lens, what would happen and where would you get the image? So let us consider the same two rays, one ray parallel to the principal axis passing through the focus, another ray passing through the optical center. When these two rays refract, they don't meet on the other side of the lens. Instead, when we extrapolate these refracted rays, they seem to be meeting in front of the lens itself. These two extrapolated rays will meet in front of the lens itself, thus forming an image A dash B dash. And the properties of the image thus formed is that the image is on the same side of the object and the size of the image is highly enlarged and the nature of the image is virtual and erect. So these are the various positions of the objects kept in front of a convex lens and the various positions where the images are formed. So mostly in front of a convex lens, if you place an object, most of the times the image is real and inverted, except the last condition, that is when you bring it close to the convex lens, you get a virtual and erect image. Next, let us see the image formation in concave lens. Here again, with the same three basic rules for drawing the image formation diagrams, in concave lens, the first position what we consider is placing an object at infinity. So from infinity, we assume only the parallel rays passing from the object. These parallel rays will diverge and these diverged rays seem to be meeting at the principal focus in front of the concave lens itself. And thus the refracted rays seem to be meeting at the principal focus where the image is formed. The position of the image will be on the same side of the object and the size of the image will be highly diminished, or simply a point-sized image will be formed, and the nature of the image will be virtual and erect because here the actual refracted rays do not meet. We are extrapolating the refracted rays to meet at a point. So the image thus formed will be a virtual and erect image. The next position is when you bring the object between optical center and infinity. When you place the object at anywhere between optical center and infinity, and again when you consider the same two rays, that is one ray parallel to the principal axis gets diverged and seem to be passing through the principal focus. Another ray passing through optical center will not get diverged. So these two refracted rays will tend to meet at a point in front of the concave lens itself, that is on the same side of the object itself. And the image always lies between optical center and focus, principal focus. So the image is always smaller than the object. So the properties of the image thus formed are: the image position is on the same side of the object, and the size of the image is always smaller, that is the diminished size, and the nature of the image is always virtual and erect, because the actual refracted rays will not meet. So we extrapolate the refracted rays so as to meet at a point to form an image. So thus the image formed will always be virtual and erect. So these are the properties of the images formed in front of a concave lens. Now let's go on to the next topic, that is uses of lens based on the image formation. Because when you place the object at various positions, you get different types of images. So based on that, we can use the lens accordingly. So first, convex lens, the applications of convex lens. First and foremost is when the object is at infinity. So with this condition, the convex lens can be used as a telescope. It is used in telescope. Then when the object is placed beyond 2f, this can be used to correct the human eye defect, and it is also used in the camera lens. And when the object is equal to 2f, that is when the object is placed at c, you get the same size and you get the same position. So such position is used in photocopiers. And when the object lies between f and 2f, the lens is used in projectors and compound microscopes. And when the object is at principal focus, then the lens is used as an astronomical telescope. And when the object is brought very close to the lens, it is used as compound microscope. Then the concave lens, wherever you place the object, you get a virtual and erect image and a smaller size image. So these type of lenses are always used in spectacles, which are used to rectify the human eye defects. Hope all of you understood the concept thoroughly. Thank you for watching.